Okay, so now we're trying to find what is the total heat balance across an electrical heat source. Let's consider a pipe. Okay, so what is the heat balance that is across this electrical pipe? Let's assume a small volume of a cylinder of a width delta R with the inner radius being R and the outer being R plus delta R. So the rate of heat transfer across R, 2 pi R actually, R is equal to R equal to 2 pi R into L into Q R. Now here all of this is at R is equal to R. Now at the rate of heat across the cylinder, sorry about that, so the rate of heat at R is equal to R plus delta R will be equal to 2 pi R plus delta R into L into Q R plus delta R. Now this would be negative because it's going outside. Now here R plus delta R can be written also as R, since delta R is very small. You can take this as R. And finally, what is the total heat being radiated, the heat of production in the small section? So that would be equal to heat of production can be written as the total volume 2 pi R delta R L into SE. Now you just have to balance this. Take this on the left hand side, take this on the right hand side, divide the whole equation by 2 pi delta R L. Here you get Q R plus delta R minus Q R whole into R divided by delta R is equal to, and this side you just have SCR. Okay, now you can take delta R tends to 0, so you get dr QR divided by dr is equal to SCR. So now you can integrate this part, and on integration you get r QR is equal to SCR square by 2 plus C1, and QR is equal to SCR by 2 plus C1 by R. Now we know at R is equal to 0, QR must be finite, cannot be infinite. So when you substitute R is equal to 0 here, you get 0 C1 by 0, which leads to infinity. So for this to actually work out, C1 must be equal to 0, or in other words, QR must be equal to SCR by 2. Now the next step, you can just write this as K dt by dr is equal to SCR by 2. Or you can write dt by dr is equal to minus SC by 2K. And you just have R outside. And now on integrating this again, you can get T is equal to minus SC by 2K to R square by 2 plus C2. Now here we know at T is equal to T0, at R is equal to R. So on substituting this value, you get C2 is equal to, sorry about that, I'm using this, T0 plus SC 2K R square by 2. So this is the second part of the equation, and now you just substitute this value inside this. So what you get is T minus T0 by SC R square by 4K is equal to 1 minus R by R square. Now this is the basic equation, and you know to get the maximum temperature, so you have to take the differential of this. So this whole differential should be equal to 0. So on differentiating, this becomes, for this to become 0, R must be equal to 0. So that means T max minus T0 should be equal to SCR square by 4K. So this is the maximum temperature. Now to find the average temperature, which is T minus T0, can just integrate this from 0 to 2 pi, 0 to r. Here it will be Tr minus T0 into r into dr into d theta, and here it will be 0 to 2 pi, 0 r. There's no t term, just be r dr d theta, and when you do this you get CR square by 8k. And finally, to get the heat flow, QR at R is equal to R should just be 2 pi RL into QR, R which you know is 2 pi RL into SCR by 2. Okay, so this is how you solve in case for a heated wire with respect to the heat generated. Okay, so let's see the next problem in the next video.